Q6509. When rolling out of a steep bank turn, what causes the lowered aileron to create more drag than when rolling into the turn? A. The wing's angle of attack is greater as the rollout is started. B. The wing being raised is traveling faster through the air than the wing being lowered. C. The wing being lowered is traveling faster through the air and producing more lift than the wing being raised. The correct answer is A. During a steep bank turn, the ailerons are used to roll the aircraft and establish the desired bank angle. As the pilot starts rolling the aircraft out of the turn and levels the wings, the ailerons are neutralized or moved to a less deflected position. This change in aileron position affects the wings and their aerodynamic characteristics. When rolling out of the turn, the lowered aileron refers to the aileron on the wing that was previously on the inside of the turn. As the rollout begins, the angle of attack of the lowered wing momentarily increases. The angle of attack is the angle between the wing's chord line, a straight line from the leading edge to the trailing edge, and the oncoming airflow. When the aircraft is in a steep bank turn, the wings are tilted relative to the horizon, and each wing has a different angle of attack. As the pilot starts the rollout, the lowered wing begins to level and align with the relative wind. However, since the wing is still producing lift while the opposite wing is reducing its lift production, the angle of attack of the lowered wing momentarily increases. An increased angle of attack on the lowered wing results in a higher coefficient of lift and, consequently, an increase in induced drag. Induced drag is a type of drag that is generated as a byproduct of lift production. It is directly related to the angle of attack of the wing. Therefore, during the rollout of a steep bank turn, the increased angle of attack on the lowered wing leads to more drag being generated by the lowered aileron compared to when rolling into the turn. In summary, the increased angle of attack on the lowered wing during the rollout causes the lowered aileron to create more drag. This is because the increased angle of attack results in a higher coefficient of lift and increased induced drag on the lowered wing. The other options are not correct because they do not accurately explain the specific reason for the increased drag on the lowered aileron during the rollout. Q6502. The tendency of an aircraft to develop forces which restore it to its original condition when disturbed from a condition of steady flight is known as A. Stability, B. Controllability, C. Maneuverability. The correct answer is A. The tendency of an aircraft to develop forces that restore it to its original condition when disturbed from a condition of steady flight is known as A. Stability. Let's delve into this concept in more detail. Stability refers to an aircraft's ability to maintain its desired flight path and attitude, even when subjected to external disturbances or changes. It is an essential characteristic that ensures the aircraft's predictable and controlled behavior during flight. When an aircraft is in a condition of steady flight, it means that it is in a balanced state where all forces and moments acting on the aircraft are in equilibrium. However, various factors, such as gusts of wind, turbulence, or pilot input, can momentarily disrupt this equilibrium and cause the aircraft to deviate from its original condition. In the context of stability, the disturbed aircraft possesses inherent characteristics that generate forces and moments to counteract the disturbance and return the aircraft to its original state. These inherent stability characteristics can be observed in three main types of stability: longitudinal stability, lateral stability, and directional stability. 1. Longitudinal stability. Longitudinal stability refers to the stability of an aircraft along the longitudinal axis, which runs from the nose to the tail. It involves the stability of pitch, which is the rotation of the aircraft's nose up or down. Positive longitudinal stability ensures that the aircraft naturally returns to its original pitch attitude after being disturbed. 2. Lateral stability. Lateral stability refers to the stability of an aircraft along the lateral axis, which runs from wingtip to wingtip. It involves the stability of roll, which is the rotation of the aircraft's wings side to side. Positive lateral stability ensures that the aircraft tends to level its wings and maintain its desired bank angle. 3. Directional stability. Directional stability refers to the stability of an aircraft along the vertical axis, which runs from the top to the bottom of the aircraft. It involves the stability of yaw, which is the rotation of the aircraft's nose left or right. Positive directional stability ensures that the aircraft naturally tends to align itself with the relative wind and maintain its intended heading. In each of these stability axes, the aircraft's design, including its wing and tail configurations, plays a crucial role in generating stability. By having inherent stability characteristics, the aircraft develops restoring forces and moments that counteract disturbances and bring the aircraft back to its original condition. Controllability and maneuverability, while related to aircraft performance, are different concepts from stability. Controllability refers to the ability of the aircraft to respond to control inputs from the pilot, while maneuverability relates to the aircraft's ability to perform various maneuvers. These concepts are important for the pilot's ability to control the aircraft effectively, but do not specifically address the inherent restoring forces of stability. 6566. The quality of an aircraft that permits it to be operated easily and to withstand the stresses imposed on it is A. Stability. B. Maneuverability. C. Controllability. The correct answer is B. Maneuverability refers to the aircraft's ability to perform various maneuvers and control its motion in response to pilot inputs. It encompasses the aircraft's agility, responsiveness, and versatility in executing different flight maneuvers. An aircraft with good maneuverability possesses characteristics that allow it to change direction, attitude, and flight path easily and efficiently. These characteristics enable pilots to maneuver the aircraft precisely and comfortably in different flight regimes, such as during takeoff, climb, cruise, descent, and landing. Here are some factors that contribute to an aircraft's maneuverability. Control response. A maneuverable aircraft has responsive and effective controls that allow pilots to smoothly and accurately command changes in attitude, altitude, and direction. The controls should provide a direct and intuitive interface between the pilot's inputs and the aircraft's response. Power-to-weight ratio. An aircraft with a favorable power-to-weight ratio can accelerate, climb, and change direction more efficiently. A higher power-to-weight ratio provides the aircraft with greater thrust or power relative to its mass, allowing for improved maneuverability. Wing design. The wing design, including factors such as wing area, aspect ratio, and wing shape, influences an aircraft's maneuverability. Wings with higher aspect ratios and sufficient lift capabilities contribute to improved maneuverability by providing better lift-to-drag ratios, reduced drag, and enhanced control authority. Flight control surfaces. The design and effectiveness of flight control surfaces, such as ailerons, elevators, and rudders, play a significant role in maneuverability. These surfaces allow pilots to control roll, pitch, and yaw motions, enabling the aircraft to execute precise maneuvers. Stability augmentation systems. While stability and maneuverability are separate concepts, certain stability augmentation systems can enhance an aircraft's maneuverability. These systems, such as fly-by-wire controls or digital stability augmentation systems, can provide stability when needed while also enhancing the aircraft's responsiveness and maneuvering capabilities. Controllability and stability, while related to aircraft performance, are distinct from maneuverability. Controllability refers to the aircraft's ability to respond to control inputs from the pilot. It involves the effectiveness and predictability of the controls in maneuvering the aircraft. Stability, on the other hand, refers to the aircraft's ability to maintain its intended flight path and attitude when disturbed from a condition of steady flight. In summary, maneuverability is the quality of an aircraft that allows it to be operated easily and withstand the stresses imposed on it. It involves the aircraft's agility, responsiveness, and ability to perform various maneuvers. Factors such as control response, power-to-weight ratio, wing design, flight control surfaces, and stability augmentation systems contribute to an aircraft's maneuverability. 6567. The capability of an aircraft to respond to a pilot's inputs, especially with regard to flight path and attitude, is A. Response. B. Controllability. C. Maneuverability. The correct answer is B. Controllability refers to the aircraft's ability to respond to control inputs from the pilot and to maintain the desired flight path and attitude. It involves the effectiveness and predictability of the aircraft's controls in maneuvering the aircraft as intended by the pilot. When a pilot manipulates the control surfaces, such as the ailerons, elevators, and rudder, the aircraft should respond in a controlled and predictable manner. The pilot's inputs should result in the desired changes in the aircraft's flight path, altitude, and attitude. Controllability is influenced by various factors, including control response. An aircraft with good controllability exhibits a direct and responsive relationship between the pilot's inputs and the aircraft's response. The controls should provide an intuitive and precise interface, allowing the pilot to command changes in flight path, attitude, and altitude smoothly. Stability characteristics. While stability and controllability are separate concepts, they are closely related. A well-designed aircraft possesses inherent stability characteristics that contribute to its controllability. The aircraft should be stable enough to resist unintended deviations from the desired flight path and attitude, while still allowing the pilot to control and maneuver the aircraft as desired. Control forces and feedback. The forces required to manipulate the controls should be appropriate and provide the pilot with a sense of the aircraft's response. The pilot should receive clear feedback through the control forces, allowing for precise control inputs and better situational awareness. Response to control inputs. The aircraft's response to control inputs should be consistent and predictable. When the pilot commands a control input, such as aileron deflection or elevator movement, the aircraft should respond promptly and accurately, allowing for precise control over the flight path and attitude. Controllability is crucial for safe and effective aircraft operation. It enables pilots to maintain control over the aircraft in various flight conditions, including takeoff, climb, cruise, descent, and landing. A high level of controllability allows pilots to handle unexpected situations, respond to emergencies, and perform precise maneuvers. While response and maneuverability are related to aircraft performance, they are different concepts from controllability. Response refers to the aircraft's ability to react promptly to control inputs, while maneuverability relates to the aircraft's ability to perform various maneuvers. 6563. The initial tendency of an aircraft to develop forces that further remove the aircraft from its original position when disturbed from a condition of steady flight is known as A. Negative static stability. B. Dynamic instability. C. Positive static stability. The correct answer is A. Static stability refers to the aircraft's initial response to a disturbance from its steady flight condition. It describes how the aircraft behaves when it experiences a disturbance and whether it has a tendency to return to its original state or move further away from it. Positive static stability occurs when an aircraft, after being disturbed, develops forces that restore it to its original condition. In other words, the aircraft exhibits a natural inclination to return to its original position without the need for constant pilot intervention. Positive static stability provides stability and helps maintain the aircraft's desired flight path and attitude. On the other hand, negative static stability refers to the opposite situation. When an aircraft has negative static stability, it initially develops forces that further remove it from its original position when disturbed. In this case, the aircraft has a tendency to diverge from its original state, requiring continuous pilot input to maintain control and bring it back to the desired flight path and attitude. Dynamic instability, as mentioned in option B, is a broader term that refers to the instability of an aircraft's motion over time. It involves complex interactions of forces, moments, and oscillations that can lead to uncontrollable or divergent behavior if not properly managed. Dynamic instability can manifest in various forms, such as spiral instability, Dutch roll, or flutter. However, it is not specifically related to the initial tendency of an aircraft to move further from its original position when disturbed. This term describes the initial tendency of an aircraft to develop forces that further remove it from its original position when disturbed from a condition of steady flight. It indicates that the aircraft requires constant pilot intervention and control inputs to maintain stability and bring it back to the desired flight path and attitude. Therefore, negative static stability represents a condition that necessitates ongoing pilot control and corrective actions to counteract the initial tendency of the aircraft to deviate from its original state.